In this video I'm going to show how to make a simple voltage sensor for the ESP32 or another microcontroller, just by using two resistors. We'll go through how a voltage divider works, how to wire it up, how to write the code, and finally test it with a lab power supply. I'll also show you how to correct a small voltage offset in the code for more accurate readings. Let's start with the basics. We're going to use a voltage divider, which is simply two resistors in series. The voltage you want to measure is applied across both resistors, and the ESP32 reads the voltage from the middle point between them. Because of that, the ESP32 only sees a fraction of the total voltage, because it's divided down by the two resistors' value. Now keep in mind, the ESP32's analog input pin can only handle 3.3 volts maximum. Anything higher than that could damage the pin, so we need to choose resistors values that safely bring down the input voltage to a maximum of 3.3 volts. For example, when you want to measure 12 volts safely, you can choose one resistor of 100 kiloohms and another resistor of 20 kiloohms, because these two resistors make it possible to divide 19.8 volts down to 3.3 volts, so you have a big range between 0 volts and 19.8 volts to safely measure your 12 volts. Because it's always good to have a bit of a higher maximum, so you can have overshoot at your 12 volts measurement and it won't kill your ESP32 or your microcontroller that has a maximum of 3.3 volts on its inputs. Now that you know everything about how a voltage divider works and we know what resistors we should choose, we're going to take a look at the schematic of the voltage sensor. So first take the first resistor and connect one side of this resistor to your voltage source positive. For example, the positive terminal of your lab power supply, in my case. Connect the other side of the first resistor to one pin of the second resistor, and connect the other pin of the second resistor to the ground. Then we're going to connect the junction between the first and the second resistor to an ESP32 analog input pin. I'll use GPIO 34. And finally, we're going to connect the ESP32 ground to the power supply ground, so both share the same reference. It's also really important to place the higher resistors value, in my case the 100 kiloohms, on the positive side of the voltage source that you want to read. And you need to place the lower resistors value, in my case the 20 kiloohms, on the negative side of the voltage source that you want to read. This is because you're going to read the voltage after the first resistor, the point between the two resistors. You want the largest voltage drop to happen across that first resistor, so the voltage at the middle point is safely reduced before it reaches the ESP32's analog input. If you flip the resistors around, the smaller resistor would be on the high voltage side. That means it would have a much smaller voltage drop and most of the voltage would pass straight through to the ESP32's input pin. In other words, instead of dividing the voltage down, you'd be sending almost the full input voltage directly into the ESP32's input pin, which will almost certainly damage or destroy your microcontroller. Now let's take a look at the code that reads the voltage. As you can see here, the first thing that we do is define the analog pin. Not every ESP32 or microcontroller pin supports analog input, so you need to make sure that the pin you choose for this analog input pin supports input. Next we define the resistors values we used in our voltage divider. R1 is the top resistor connected to your voltage source, and R2 is the bottom resistor connected to the ground. The junction between them goes to the analog input pin that we defined previously. Now in the loop function, we start by reading the analog input. This gives us a number between 0 and 4095, since the ESP32 has a 12-bit analog to digital converter. More about this later. Next we convert that number to the voltage the ESP32 actually sees. So we divide the raw input value by the maximum value of the analog to digital converter and multiply this value by the maximum voltage that the ESP32's pin can handle, so 3.3 volts. And finally, we calculate the real input voltage before the divider, and then we print the results in the serial monitor. So what happens in this code? The ESP32 uses a 12-bit analog to digital converter, which means that it converts the analog voltages into digital values between 0 and 4095, because this is the maximum range that the 12-bit can reach. So 0 represents 0 volts and 4095 represents 3.3 volts. So let's test this code. I've connected my lab power supply to the voltage divider input, and the ESP32 is running the code we just wrote. As you can see here on the serial monitor, when I slowly increase the voltage on the power supply from about 5 to 12 volts, the values on the serial monitor follow right along. But there's a small difference. This difference is just a tiny offset, which happens because of a couple of reasons. One of them is the resistor tolerance, because the resistors are not ideal and can vary a bit in value, or the analog to digital converter calibration of the ESP32, or just minor electrical noises can all have some influence on this offset. To fix this, we can simply subtract the offset in our code. So let's add another line to define the offset's value, and then in our loop, when we calculate the final voltage, we adjust it like this. So we subtract the offset from our calculated value, and the rest stays the same in the code. Now when we look at the serial monitor again, the readings almost perfectly matches the power supply voltage, even as you change it. So let's change it from 5 volts up to 12 volts, and you can see that the serial monitor almost perfectly matches the power supply voltage. That means our offset correction works. Important to keep in mind when setting an offset is that when you add an offset in your code, you're changing the value that's being shown on the serial monitor. You're not changing the real voltage on the ESP32's pin. For example, with a 100 kilo and 20 kilo voltage divider, your ESP32 reaches 3.3 volts on the input pin when the measured voltage is about 19.8 volts. Now, if you see a negative offset in your serial monitor, for example, minus 0.4 volts, the code will already display 19.8 volts when the real voltage is only 19.4 volts. That means the ESP32 pin is already at its limit of 3.3 volts when the input is 19.4 volts. So if you go any higher, you'll actually go over the safe range. And the positive offset works the other way around. It makes the voltage reading look a bit lower than the real value, which won't damage anything, but it does make your reading less accurate. So remember, a negative offset makes your safe input range smaller, because the ESP32 reaches its maximum voltage earlier than you think. Let's quickly summarize what we've done. We've built a voltage divider using 2 resistors to safely measure higher voltages. We've wired it to an ESP32 or another microcontroller's analog input pin. We've wrote code to read and calculate the actual input voltage. And we've learned about the 12-bit analog to digital converter that the ESP32 has and how it converts analog voltages into digital values. And we've tested the setup with the lab power supply and fixed a small offset for accurate results. And that's it, you've just made your own ESP32 voltage sensor without needing any pre-made modules. It's simple, accurate, and a great way to learn how analog inputs work on microcontrollers. I hope this was helpful, and thank you for watching.